Hi, Honors Algebra 2 students. Welcome to Chapter 8, Day 1 of Notes. In this lesson, we're going to focus on simplifying radicals. All right, so our instructions say simplify the following radical expressions. And in the first example, you can see here that we have a 3 times the square root of 2 times 4 times the square root of 10. I'm just emphasizing there that everything's being multiplied together. So when that's the case, we can take the values that are on the outside of the radicals and we can multiply those together. So 3 times 4 is obviously 12. And then we can take the things that are underneath the square root and multiply those together and leave those initially underneath the square root. So what I mean by that is root 2 times root 10, or the square root of 2 times the square root of 10 is going to be root 20, or the square root of 20, if we want to phrase it that way. And as long as they are the same root, so these are both square roots, we can multiply those together and leave those under the square root symbol. Now we'll go through and we'll simplify some more, but we can initially multiply those together. Just on a side note, if this had been the cube root of 2 times the cube root of 10, we could have multiplied those together because they were both a cube root. That would be the cube root of 20. If one is a square root and one is a cube root, we can't multiply them together straight up like that. But as long as they're both the same root, in this case square root, it'll be the square root of 20. If it was a cube root, it would be the cube root of 20. All right, now we should always simplify our final answers as much as possible. So as we look at this square root of 20, we'll leave the 12 out there. Square root of 20 could be simplified to 2 root 5. And the reason for that is initially the square root of 20 is the square root of 4, times the square root of 5. Well, obviously, square root of 4 is 2. So when we simplify root 20, that will become, in the end, 2 root 5. If you need to write it like this initially, you may, but then you can simplify it to this. If you can go straight from the square root of 20 to 2 root 5, that's completely fine. All right, and then finally, for our final answer, we're going to take this 12 times 2, multiply that together, so our final answer will be 24 root 5. All right, so in our next example, we are going to simplify the square root of 48. Now, the largest perfect square that's a factor of 48 is 16. So square root of 16 times square root of 3 then becomes 4 root 3. That will get us to our answer the quickest. Now, some of you may be saying, okay, well, I would have thought of simplifying initially square root of 48 into the square root of 4 times the square root of 12. Could I have done that? Absolutely, you can start with that. That would become then 2 root 12. But if you notice, we've got factors of 12 that are perfect squares, so we could keep going. So square root of 12, square root of 4 times square root of 3. Square root of 4 is obviously 2. If I keep simplifying that, I will get to 4 times root 3 as my final answer. So as long as you recognize that you're not done when you get to this point, because there are factors of 12 which are still perfect squares, and you can keep going with simplifying. As long as you keep going, you'll get to the most simplified final answer, which is 4 root 3 in this particular case. Now, obviously, if you look for factors of 48, one of which is a perfect square, and you find the largest perfect square first, you're going to get to your answer a little more efficiently. But as long as you keep going, if you had started with root 4 times root 12, which is fine because 4 is a factor of 48, and it is a perfect square. As long as you keep going with simplifying, you'll get to the same final answer. All right, now you'll notice on this next one, we're simplifying the cube root of 48, not the square root of 48. So on the one on the left, the one that we just did, we looked for factors of 48, one of which was a perfect square, which 16 is a perfect square. That would get us to our answer the most efficiently. 4 is also a fine starting point because 4 is a perfect square also. All right, well, when we start to work with cube roots, we need to make sure we know what our perfect cubes are. You're probably very familiar with your square roots. You may not be as familiar with your cube roots. So the way you can figure out what your perfect cubes are is you could think about them as follows. Now, I wrote 0 cubed and 1 cubed on here, but they're not going to help us in any way. Because sometimes if I start with 2, students are like, why did you start with 2? Well, 0 cubed is 0, 1 cubed is 1. Rewriting anything in terms of those is not going to be helpful. So 2 would be the large or smallest number that we could start with that would actually help us. So 2 cubed is 8. 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216. So in other words, the numbers that are on the right-hand side are perfect cubes, but that is where those numbers come from. Yes, we could keep going, 7 cubed, 8 cubed, etc. But I would say as long as you know up through 6 cubed being 216, or the fact that 216 is a perfect cube, then you'll be okay with the problems that we're working, and you should be doing them without a calculator. So as long as you have these memorized and you know what they are, you'll be in good shape to do the majority of the problems that we're doing. Now, if you needed to know what 7 cubed was, you could easily figure that out. You could calculate it, but I would say that you should know these just right off the top of your head. So now what we're going to do, we're going to look at this list and we're going to figure out factors of 48, and we want to look for a perfect cube because that will help us simplify this cube root. So if we look at our list over here, 8 is a perfect cube. Well, 8 is a factor of 48, so that's going to be the one that will help us. So I could rewrite the cube root of 48 as the cube root of 8 times the cube root of 6. Obviously, 8 times 6 is 48. If we're talking with a cube root of 48, we need to write it as the cube root of 8 times the cube root of 6. All right, well, what is the cube root of 8? Cube root of 8 is 2, because that's what I multiply by itself 3 times to get 8. 2 times 2 times 2 is 8. So the cube root of 8 is 2, or in other words, if we're looking at it over here, since 2 cubed is 8, the cube root of 8 is going to be 2. And then there's nothing more that we can do to simplify the cube root of 6, so that will be our final answer, 2 times the cube root of 6. That is the simplifying of the cube root of 48 that we started with. All right, so now if we look at our next example, we're simplifying the 4th root of 48. So as you might imagine, we need to know our perfect 4th roots. So 0 and 1 aren't going to help us. Okay, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256, 5 to the 4th is 625. That would be a good list for you to memorize. Make sure that you can easily know those because that will make your simplifying process as we work through it much more efficient. So in other words, if we look at the right-hand side of these equations, knowing that you can take the 4th root of 16 and get 2, and the 4th root of 81 and get 3, and the 4th root of 256 and get 4, and the 4th root of 625 and get 5, that's what's going to be helpful to you. All right, so if we once again look at our list, we need to pick one of these values that is also a factor of 48. In other words, that's what's going to help us. So if we look at our list, 16 is a factor of 48. So we could rewrite the 4th root of 48 as the 4th root of 16 times the 4th root of 3. All right, well, the reason that's going to help us is because the 4th root of 16 is 2, and then the 4th root of 3, there's nothing more that we can do to simplify that. So that will be our final answer. When we simplify the 4th root of 48, it is 2 times the 4th root of 3. All right, now before we go on to our next examples, I want us to take a look just briefly here at the square root of 48, the cube root of 48, the 4th root of 48. As you can see, we got 3 entirely different answers. All right, if you look at the answer we got for the square root of 48 versus the cube root of 48 versus the 4th root of 48. I don't need to read those to you, but you can see that they are entirely different. But what I want to emphasize is that the process is the same. So you're very familiar with working with square roots, so you may not even think about the process, but what you're trying to do is you're trying to rewrite the square root of 48 into factors of 48, one of which is a perfect square. So that would be the square root of 16 times the square root of 3, and then we kept going with simplifying. When you try to simplify the cube root of 48, you want to rewrite the cube root of 48 into factors of 48, one of which is a perfect cube. So the cube root of 48 is rewritten into the cube root of 8, because that's a perfect cube, times the cube root of 6, and then we could go through and simplify. And then finally, when we rewrite the fourth root of 48, we want to be able to rewrite that so that we can take, we want to rewrite it into factors, one of which we can easily take the fourth root of. So the fourth root of 16 times the fourth root of 3, that helps us because the fourth root of 16 is 2, and we can keep going with simplifying. So the process is the same. You may, again, be very familiar with doing it with square roots, so you don't even think anything about it. But the process for simplifying cube roots and fourth roots is going to be similar, but instead of looking for perfect squares that are factors of the given number underneath the radical, you are looking for factors, for example, that are perfect cubes of the number that's underneath the radical. All right, in the next example, you may notice that we have the square root of 27 minus the square root of 75. So in the first example that we did, we were multiplying radicals. In this particular example, we are subtracting radicals. So the process that we're going to go through would work whether we were adding or subtracting radicals. What we first need to do is we need to simplify each one of these radicals, because here's the thing, we cannot take the square root of 27 and subtract the square root of 75. They are not like radicals. They're both square roots, but they're not both a square root of 27 or both a square root of 75. So what we want to do first is we want to simplify each one of these radicals individually, and then we'll see if we can do our subtracting. Same process would be followed if we were adding radicals here as opposed to subtracting them. All right, so if we simplify the square root of 27, that will be 3 root 3. If we simplify the square root of 75, that would be 5 root 3. And again, the reason for that, and you can write out an extra step if you need to, but the reason for that is that the square root of 27 can be rewritten as the square root of 9 times the square root of 3. Well, the square root of 9 is 3, so that would simplify to 3 root 3. Similarly, the square root of 75 is the square root of 25 times the square root of 3. Well, the square root of 25 becomes 5, so 5 root 3. Okay, so now that we have simplified the square root of 27 and the square root of 75, now we can look at these two terms. Well, if you notice, they're both root 3's. So if they're both root 3's, we can do our subtraction right here. So what we're going to do is we're going to leave the root 3 the same, but we are going to take the coefficients, 3 minus 5, and get negative 2. So our final answer is going to be negative 2 root 3. In other words, if we have a 3 root 3 minus a 5 root 3, that gives us negative 2 root 3. We're going to leave the root the same, all right, and then we're just going to, in this case, subtract the coefficients that are in front of that root 3. So think about it this way. It would be like taking 3x minus 5x. That would be negative 2x. We leave the x the same. So we can now subtract these terms because the roots are the same. They're both square root of 3. And since they are both the same, we can take the coefficients, do our calculation, and then leave our root the same. Final answer, negative 2 root 3. Now we're going to go through a similar process that we just did for square roots, and we're going to apply that to cube roots. So the first thing we need to do before we can subtract the cube root of 250 minus the cube root of 54, we need to simplify the radicals as much as we possibly can. So going back to what we learned about simplifying cube roots, we need factors of 250, one of which is a perfect cube. So the cube root of 125 times the cube root of 2 is equivalent to the cube root of 250. The cube root of 125 is 5, so the cube root of 250 is going to simplify to 5 cube root of 2. All right, so now I'm going to go through a similar process for simplifying the cube root of 54. I need factors of 54, one of which is a perfect cube. Well, 27 is a factor of 54, and it's a perfect cube. So the cube root of 54 can be rewritten as the cube root of 27 times the cube root of 2. 27 times 2 is obviously 54. So the cube root of 54 is rewritten as the cube root of 27 times the cube root of 2. Well, the cube root of 27 is 3, so we'll have minus 3 cube root of 2. All right, so at this point, I have simplified the cube root of 250. I've simplified the cube root of 54. And if you notice, I've got 5 cube root of 2 minus 3 cube root of 2. So the key thing to note here is that I have the same radical. I've got 5 cube root of 2 minus 3 cube root of 2. The cube root of 2's are the same. So since that is true, I can now take the coefficients and I can do my subtracting. So my final answer will be 5 minus 3 gives me 2, so 2 cube root of 2. That will be my final answer. All right, so the key thing is that you can add, if these have been addition problems, which I know they weren't, but if these have been addition problems or you saw them as subtraction problems, I can add and subtract radicals once I have the same radical. So once I change these on the left here to be root 3's, I can do my adding or subtracting in this case. Once I found that these were both cube root of 2's, I could then do my subtracting. All right, and one final thing to note from this. If I had simplified the radicals in these last two problems, and one had been, for instance, a square root of 3, and one had been a square root of 2, for example, I would have had to have left those as separate terms. I could simplify each term individually, but I wouldn't have been able to do my subtracting, or if the radicals are different, I can't do my adding either. I would just have to leave them as separate terms for my final answer. All right, in our next example, we're going to simplify the square root of 27 times x to the 7th. And I think you would readily say that square root of 27 would simplify to 3 root 3. And that is correct. What I'm going to do, though, to simplify x to the 7th, and there are many ways in which you could do this. So if you know another way from a prior class, you can certainly use it. But one way that I typically show my students on this example is I say, okay, well, let's rewrite x to the 7th in the following fashion. X squared times x squared times x squared times x to the first. And the reason I do that, well, first of all, let's notice the following. If I'm multiplying something that has the same base, I can add the exponents. So 2 plus 2 plus 2 plus 1 gives me 7. So I can rewrite x to the 7th as I did right here. Well, how is that going to help me? Well, each one of these x squareds, the square root of x squared is going to be x. So the square root of x squared is x. If I go to the next one, the square root of x squared is another x. The square root of x squared is another x, and then I'm left with the x that's underneath the radical. So in other words, the square root of each one of these x squareds became an x that was on the outside of the radical. And then if I go through and simplify that completely, I'll have 3x cubed times the square root of 3x. And notice in this case, not only did some of my numbers come outside the radical and some stayed underneath, but some of my variables came outside the radical and some stayed underneath. So this would be my final answer. Now, again, there are various ways in which you could go through and simplify that, and you may know another way and like your method better, and that's fine. You may use it. But this is one way in which we could go through and simplify the original problem that we were given. All right, and then one more thing. This was obviously a square root, so I broke these down into x squareds. If this had been a cube root, I would have rewritten x to the 7th in terms of x cubed, because the cube root of x cubed would be x. So, you know, if this had been written in terms of cube roots, this would have looked a little bit different down here. It would have been x cubed times x to the first. Again, the exponents would have added up to 7, but taking the cube root of x cubed, that would be just x. In other words, that would have been a perfect cube. So take a look. Again, it's important to take a look, just like we were looking above, to see if you're working in terms of square roots or cube roots or fourth roots or whatever the case may be. And then you can rewrite the variables in terms of those exponents accordingly. All right, in our next example, you'll notice that we have a radical in the denominator. So we are going to rationalize the denominator and get rid of that radical. If you notice, though, we have two terms in our denominator. So when we go through and rationalize that, we're going to rationalize that by taking the conjugate of the denominator. And we've talked about conjugates earlier in this course. So the conjugate of the square root of, the square root of 6 plus 1 would be the square root of 6 minus 1. And whatever I multiply the denominator by, I'm going to multiply the numerator by. And the reason I'm doing that is because now essentially I'm multiplying this expression by 1. So I'm not overall changing it by multiplying it by 1. A different version of the number 1, but the equivalent of 1 nonetheless. So again, I'll look at my radical in the denominator. I will multiply by its conjugate, what I multiply the denominator by. I obviously need to multiply the numerator by. All right, so then if I go through and do my multiplying, keeping in mind I've got a binomial in both the numerator and denominator that I'm multiplying by. Sometimes when I go through and multiply the numerator, sometimes I will just leave it written, not distributed initially for simplification purposes. So I will just leave it written as 2 times that binomial square root of 6 minus 1 for right now. If I go through and FOIL the denominator, the first terms will give me 6. The outside terms will give me negative square root of 6, the inside terms plus square root of 6, and then the last terms minus 1. Now, you may have gone through and just done this in your head and realized that the negative square root of 6 plus square root of 6, that those were going to cancel each other out, and that's fine. If you have picked the correct conjugate and done your FOILing correctly, that is what should happen. You should get rid of the radical in your denominator for sure. All right, so the numerator will be 2 square root of 6 minus 2. I'll go ahead and distribute that now. If you distributed it earlier, that's fine also. And then my denominator will simplify to 5. So this will be my most simplified answer. 2 square root of 6 minus 2, all divided by 5. Okay, if you look at our next example, we have 2 divided by the square root of 5, and we want to rationalize our denominator so we do not have a radical left in our denominator. And you've probably done these before, and you simply multiply by the square root of 5 divided by the square root of 5. And that's fine. You know, we don't have 2 terms in our denominator like we did in the prior example. And sure enough, if we multiply by square root of 5 divided by square root of 5, we're essentially multiplying by 1, so that's fine. And that will get us to 2 root 5 divided by the square root of 25, which obviously is a perfect square, so our final answer is 2 root 5 divided by 5. And in fact, you may just jump straight from multiplying it by root 5 over root 5 to your final answer, because you know that square root of 5 times square root of 5 is going to be 5, and that's completely fine. I wanted to go through the process, though, of this particular example because of what we're going to be doing on the one to the right in just a moment with a cube root. But to finish this one off, this would be our final answer. One thing I will say is that you should always take a look once you've rationalized the denominator and gotten rid of your radical. For instance, it became the number 5. You should always look at the numbers on the outside of the radical to see if you can further simplify them. Now, 2 divided by 5 will not simplify as a fraction, so we'll just leave it as is. But if that had been something that you could further simplify as a fraction, you should go through and do that. Okay, now when we do the next example, 2 divided by the cube root of 5. All right, over here, the reason we multiply by the square root of 5 is because that got us to the square root of 25, which was a perfect square, so that when we took the square root of it, we just got the number 5. So since it was we needed to work to a perfect square, we needed 2 5s underneath the radical in order to get to that perfect square of 25. So when we decide what we're going to multiply by for this next example, we need to work our way towards a perfect cube root. All right, so a perfect cube root in this case would be when we have 3 5s, okay? In other words, that would be the cube root of 125 in the denominator, if you want to think about it that way. So what will we need to multiply by? Well, if we're starting with 1 5 underneath a cube root, and we need to get to 3 5s underneath that cube root, and the reason we need to get to 3 of them is because then we would have a perfect cube. And in fact, you may not even go through this step. You might just say, well, the cube root of 3 5s is going to be 5, which is true. Okay, the cube root of 3 5s is going to be, in this case, 5. If you go through this intermediate step, yes, the cube root of 125 is 5. Okay, well, what would we need to multiply by? Well, if we start with 1 5 underneath the cube root, we would need to multiply by 2 more of them. And the reason for that is we started with 1 5 underneath the cube root. If we multiply by 2 more 5s underneath the cube root, that will give us 3 5s underneath the cube root, and that will then indeed be a perfect cube. Whatever we multiply the denominator by, we need to multiply the numerator by. Now, I'm just going to go ahead and say that we are multiplying by the cube root of 25, because obviously we are multiplying by the cube root of 25. The cube root of 5 times 5 is the cube root of 25. All right, so if we go through and keep simplifying a little bit, notice that in the numerator here we had 2 times the cube root of 25, and that will just keep carrying through to our final work. I'm just going to keep rewriting this. All right, so let's take a look at what we have. We have 2 times the cube root of 25 divided by 5. We cannot simplify the cube root of 25 anymore. In other words, there are not factors of 25, one of which is a perfect cube, so we cannot simplify that anymore. And 2 divided by 5, we cannot simplify that anymore as a fraction. So our final simplified answer will be 2 times the cube root of 25, all divided by 5. All right, so before we finish off this lesson, I want to go back and just summarize what I did in these last 2 examples. Having said that, feel free to ask about these in class. Usually after students have seen just one example of each of these, while they're familiar with the square root, they're not as familiar with the cube root example that I did. So often you may need to ask follow-up questions. Please feel free to ask your teacher in class to clarify anything that you may not have understood. All right, but having said that, the reason on the left-hand side that we multiplied in the denominator by the square root of 5, the reason we chose that is because then we would have 2 5s underneath the square root, and that would give us a perfect square. Obviously, when we take the square root of 2 5s underneath the radical, we're going to get just the number 5. And obviously, whatever we multiply the denominator by, we have to multiply the numerator by. All right, now we did a similar process in the example on the right. If we have the cube root of 5 in order to work our way to a perfect cube, on the left we needed to work our way towards a perfect square. On the right we need to work our way towards a perfect cube. So we need 3 of something. So if we have 1 5 underneath this cube root sign, if we multiply by 2 more 5s, we would have 3 5s, and the cube root of 3 of anything will just be that anything. So the cube root of 3 5s is just going to be 5. And whatever we multiply the denominator by, we need to multiply the numerator by, and then we went through the simplifying process. Now, do you need to write out this intermediate step right here? No, you do not need to. If you want to go straight from what I have written here to your final answer, that's fine. Same thing over here. If you want to write out this intermediate step right here, that's fine. If you want to go straight from this step up here to your final answer, that's fine. The main reason I wrote this intermediate step on the one on the left is so that you could see the comparable step over here to the right. Now, the final thing I want to say about this one to the right, sometimes students will just say, well, I want to go from the cube root of 5. I know I need to get to the cube root of 125 because 125 is a perfect cube, and 125, 5 is a factor of 125. So I can get there by multiplying both the numerator and the denominator by the cube root of 25. And sometimes they'll think through it that way. Instead of breaking it out into these, 3 5s over here, so therefore I have to multiply by 2 5s because I only started with 1 5 underneath the radical. Sometimes they'll think it through it that way. What's a perfect cube that 5 is a factor of? Well, that would be 125. So how do I get from the cube root of the cube root of 5 to the cube root of 125? Well, I'm going to have to multiply by the cube root of 25. So that's how they'll go through that thought process. Obviously, that's completely fine. Different things are going to resonate with different students. So you figure out the thought process that resonates the best with you, and you may use it and show your work accordingly. Okay, so this wraps up Chapter 8, Day 1 notes.